Okay, so welcome to the third session, which we have called Performance versus Abstraction, for reasons which may become apparent. The first speaker is Prabhat Totoo, who will be telling us about Haskell versus F# versus Scala from various perspectives.
Hello. Yeah. Okay. Today I'm going to talk about some experiments we have been carried out over the last few months with these three languages: Haskell, F#, and Scala. So basically, this is a language comparison paper, and the goal is basically comparison of parallel programming support in these three languages in terms of performance and programmability. And in the paper, we look at the key language features that are helped in writing parallel programs, and also we emphasize a lot on high-level abstraction for parallelism. So we implemented a number of embody versions, embody problem versions, which we use as basis for comparison between these three languages. So in this talk, I will briefly go through the performance, probability, and pragmatic aspects of these three languages. So motivation. Functional languages hold a lot of promises for parallel programming, and as we all know that with properties such as referential transparency due to absence of side effects, this makes writing parallel program easier in functional language than writing an imperative language where we run into all sorts of problems such as race conditions and all. So functional programming usually encourages immutability, so it helps to, it is easier to write parallel programs. And also other key features of functional languages are that they allow high-level abstractions, and they offer a high degree of expressiveness as well through features such as high-order functions and functional composition. And we can easily define skeletons that encapsulate common parallel patterns. So we basically just have to specify what instead of how to compute something in a functional language. And this is just a quote from Simon Pittenberg, who is in the room here. He says the future of parallel is declarative. To recent trends in language design, we see that mainstream languages are integrating more and more functional features in the design. And for example, we have generics in Java and lambda expression in C# and C++ and delegates in C#. So these kind of functional features, they improve expressiveness in the language by providing functional constructs. And we also see that there are currently a new kind of paradigm, multi-paradigm languages, which makes functional programming more approachable. Like there is F#, which is a kind of functional-oriented language, but also has imperative and object-oriented constructs. And the same Scala, which is targeted for the JVM, but it starts from object-oriented, but also has a lot of powerful functional features in the language. And the other trend is that we see that there is a lot of library support for parallel patterns and also known as skeletons. Or skeletons mainly abstracting parallel computation by hiding low-level details and providing basically a familiar interface to the programmer. So we have, like, for example, TPL and many other skeleton libraries. So I'm going to quickly go through the main similarities and the difference between the three languages that we compare here. As we all know, Haskell is a pre-functional language and lazy semantics, whereas the two other languages have strict semantics. And F# is .NET interoperable, and for Scala it's Java interoperable. In terms of parallelism support, we will cover these a bit more in the next few slides. So I think I will not go through this. This is, I think everyone knows. So in terms of parallel support, in Haskell first, Haskell provides support for semi-explicit parallelism through the Glasgow parallel Haskell extension. GPH basically extends the GHC compiler by providing two basic primitives, one for parallel composition and a second one for sequential composition. So the first one, par, is just a primitive function. So it takes two arguments, and basically it says that it just marks the first argument to be potentially evaluated in parallel with the second argument. So basically what it does is just create a sparks. A sparks is kind of a pointer which hints the runtime system that it could potentially benefit by running the first expression in parallel. And so this is potential and not mandatory parallelism, so it's up to the runtime to pick up which expression is going to run in parallel. But since we need a second primitive because Haskell, we don't have any doesn't define any order of evaluation, so we need some kind of enforced sequential ordering so we can make arrange parallel computation. So this is what the second primitive is for. So this is a simple example of how you could use the par and seek primitives. So if you have a function f and there's a computation S1 and S2, and you want these two to happen in parallel, what you do, you just do S1 par S2. So it sparks S1 to be potentially evaluated in parallel, and then you need the PC, so you spark the S2 as a parallel computation. And so we have further abstraction that are built on top of these basic primitives, which is called evaluation strategies. So evaluation strategies separates the coordination aspect from the main computation. So basically it introduced a function called using that, as you can see here, which you can have an expression, say, using, and then the strategy. The strategy actually define the parallel strategy, how to proceed with evaluation. Like in this example, we can easily define a parallel map using strategy. So this is map function f on the list access. So this is just a sequential map. If we just put these three last words in the program, what basically does is just turn the map into a parallel map function. So par list is a higher order strategy which takes a strat, which is basically specify the evaluation degree to evaluate the element in the list. And par list will spark each element of the list using the given strategy. So basically it says to evaluate each element in the list in parallel and to fully evaluate the element if we use our deep seek, which specify the evaluation degree. So there are other abstractions for parallelism in Haskell. There is par monad, which is a fairly new parallel programming model which is built using concurrency primitives in GHC, and it preserves determinism, and it is quite a more explicit approach compared to GPH, but then you can fork and spawn parallel tasks, and then you need to synchronize communication between them using IVOS and put and get for communication between different parallel tasks. And you can further abstract on these communications by building skeletons like parallel map. And there is also DPH data parallel Haskell, and which is mainly to exploit data parallelism, and which is very good for both regular and nested data parallelism. And Eden is based on the concept of process, so basically it abstracts function as a process which can be which is distributed to the available processor to be run in parallel. So it is similar to lambda expression, but it is actually meant mainly for distributed memory parallelism. And the message processors communicate by each other by passing messages, but all these is hidden in the implementation. It is implicit. And we could also use it on shared memory machines. So F#, as I said, F# is a functional oriented language, like an XML-like language with object-oriented extension. And one thing that you can do in F# is, unlike Haskell, you can have mutable variables. So there is a distinction between value and variable in F#. So in terms of parallelism support, the F# actually benefits from the .NET Parallel Extension Library, or from the .NET platform, which actually provide high-level construct to write and execute parallel programs. And one of the main library under this extension is the TPL, which hides low-level thread creation, management, and scheduling details in the library. And the main concept of TPL is that of a task, which is like the main construct for task parallelism. So task basically provides high-level abstraction compared to working directly with tasks, and you can have like tasks that also returns result that is basically a future. And there are two other constructs like the parallel class, which provide static method like for parallel.for each, which is basically used for basic loop parallelization. And there is also pinlink, which is a more declarative model for data parallelism. So both of these parallel class and pinlink are actually uses tasks internally. And there is also asynchronous workflow, which is mainly intended for concurrency. So basically what you can do, you could just wrap a piece of code using the async keyword that would, which could provide basic parallelization. So Scala basically designed to be a better Java, multi-paradigm, and strict. So one thing is still very tied to the concept of objects. And okay, so in terms of parallel support, again, there are two frameworks in Scala. The first one, parallel collections framework, which is mainly intended for implicit data parallelism. So basically, in Scala, what you could do if you have a collection, you can they have a sub-package parallel for most of the collection that they have, and you could invoke it by doing like the collection. Say access is a list, so you can just do .par, which invokes the parallel version of the list, and then all subsequent operations that you invoke on this version of the collection will have a parallel implementation of the operation that you call. And this is built on top of the fork join framework, and it has a thread pool implementation that schedules tasks among available processors. And there is also the actors in Scala, which is a message passing model, so no shared state. It's very similar to the concurrency model to Scala. And there's lightweight processors that communicate by exchanging asynchronous messages. So messages basically go into mailboxes and processed using a pattern matching way. So, what we did for comparing these three languages, and we implemented the n-body problem, which is basically a problem for predicting and simulating the simulation of a system of n-bodies. So the problem has proceeds over a number of time steps, and in each time step we calculate the acceleration of each body with respect to the others, and then update the position and the velocity. So there are basically two solving methods. The naive method is to use the Orthez method, which does a direct body-to-body comparison, which is not very feasible for large n. And then there is the Barnes and Hot algorithm, which is a more advanced but efficient approximation method. So it consists of two phases: the tree construction phase and then the force calculation phase, which is actually the most compute intensive phase. So once we have a tree constructed from the list of bodies, we then for each body we traverse the tree to calculate the acceleration for each of them. So the force calculation is independent for each body. So our approach is basically we start off with a very sequential implementation and trying to preserve opportunities for parallelism by not using features such as mutable states, or so we could easily parallelize the algorithm. And we apply a number of generic optimizations, such as deforestation, which elimination of multiple traversal of data structures, and tail call optimization, and compiler optimization. Like all of the free compilers have several optimization. So first, with the Haskell implementation. So Haskell, since it is lazy, the first initial implementation we run into Stack Overflow, and then we made sure that all functions are tail recursive in an attempt to fix this problem. But then still the runtime was still very high. So what we did is to add strictness annotation where required. But then we also found that by use strict fields in the data types and pack pragma in data types definition also really help to decrease the memory consumption and improve the runtime. And we use other generic optimization. This one is more specific to Haskell, like the for and build shortcut fusion. So as I said earlier, once we build the tree, all the parallel, the second step in the Barnes and Hot algorithm is about the force calculation. So this can happen independently for each body. So basically, the algorithm present a data parallelism at the top level. So what we do, we introduce parallelism at the top level map function. So this is the core parallel code for Haskell, where we have a map FBS. BS is basically the list of bodies, and F is the function that actually, after having built the tree in the one iteration, update the velocity by traversing the tree, and then update the position. So we use a different strategy here called parallelism. So from the one that I explained earlier, so parallelist basically creates a spark for each element in the list. So this can create more overhead and too fine-grained parallelism if the actual F function doesn't perform enough work. So it is important to use some kind of chunking strategy to control the granularity. So we do not want to have too many small tasks, but then not too too few large tasks. Otherwise, there will be processors that will not have enough work to do. So basically, the list chunk strategy takes an additional parameter, chunk size. So the chunk size specifies if we have a large list of 1,000 elements, it breaks that list into smaller chunks. And then instead of creating sparks for each element in the whole list, we create spark for each chunk, thus minimizing the overhead. Yeah, so this is basically how we implement the parallel map in the Haskell code for the embedding problem. And for F#, we started off basically with a Haskell version which we optimized quite efficiently, and then we translated the code into F#, which was fairly easy and mostly syntactic changes, and we applied some general optimizations which also applied to the Haskell version, but then some more specific F# optimization, such as inlining, which in Haskell I think is done by the compiler already. And so these are the three different way of introducing parallelism in Haskell. So we could easily implement a parallel map using, for example, asynchronous workflows. So the power map async fxs is the list. So we mark each element of the list, apply the function on each element of the list by marking them with the async keyword, and then we say async parallel to turn this in as a parallel computation, and then we say synchronously to wait until all the parallel work is done. And this one, the TPL, is we try to use explicit task creation for each element in the list. This is very inefficient actually. So we are creating too many tasks. Like if we have a large list and we create a task for each element, that is not very efficient. But basically, we just wanted to compare the overhead of creating a task in F# with the overhead of having sparks in GPH in Haskell. And pinning is a more declarative way, so it's very easy it has like an SQL like syntax, so it's very easy to parallelize. Like the select is basically the equivalent to the map function, and just to have the parallel implementation, we just need to say as parallel. So yeah, in F# we can also have use parallel for, but then basically this is a more imperative style of programming F#. And parallel tuning in F#, we have maximum degree of parallelism, which specifies the maximum number of concurrently executing tasks, and we also have chunking and partitioning to control the granularity of the task. So again, for Scala, we try to translate Haskell in F# implementation into Scala and keeping the code much functional as possible. And one of the main optimizations that we did with the Scala version is remove unnecessary object initialization, because object Scala as it is still has object, it can create quite a lot of overhead. So this is an example of having the parallel collection, so very similar to pinning. So you just need to, bodies is the list, so you just do .par, which invokes the parallel version of the map. And this is like an implementation using features from the actor model. So kind of similar to creating a task for each element in the list as the TPL version. So the result, so we take measurements on both Linux and Windows, and the Windows machine is slightly faster processor compared to the Linux one, and we use the same version of GSC on both platforms, same version of F# and Scala JVM, but on Linux we use Mono instead of the .NET F# implementation. And we use 80,000 bodies and one iteration as input. So initially this is the sequential runtime that we got from running the sequential program. And this is before any optimization that I mentioned before. So after applying all the optimization to the that I mentioned, we get this. The runtime is Haskell is 25 seconds, 21 seconds for F# and 39 seconds for Scala, but on different platforms. So this is the complete on all platforms what the results are. And as you can see, Haskell is the fastest on both platforms, and for some reason, F# mono implementation on Linux isn't very efficient, and we don't get very good performance. And Scala, okay performance on Linux, but on Windows, the performance is not that good. And this is the parallel runtimes. And so I have chosen only the best implementation. Each parallel contracts that give the best runtime. So as you can see, Haskell scales quite well, and up to 8 core, it's like 4 seconds, and even on the Windows machine. But the other languages scale, but not that well compared to Haskell. And this is the speed-ups graph on Linux 8 cores. So the dotted ones are, as you can see, the red one is Haskell, and Haskell gives quite good performance. Then the second one is Scala, and F# is the last one on the Linux. And what we try to do, because F# and Scala wasn't getting as good performance as Haskell, we try to selectively use some improved features, like trying to use mutable data structure just in an attempt to improve the runtime. So we have an F# improved implementation that uses array and the parallel for, and it gives okay performance. And we did the same for Scala in improved version, but it didn't get that good performance. And on Windows machine, which is only a 4-core machine, so again, Haskell scale the best compared to the other languages. So, as I said, Haskell outperforms both F# and Scala on both platforms, and well, this has been possible after many optimization, but we did apply the same optimization to the 2 of the languages, and proof performance F# on Mono and Scala on Windows. And some of the programmability issues is in Haskell is especially to understand the implication of laziness. It's very hard to estimate how much work is involved and when expression actually get evaluated. But in general, it is easy to introduce initial parallelism. But for Haskell, we require to do some chunking, but pinning and parallel collection are more implicit, and we don't really need to do any of this. F# and Scala retain much control in the implementation. And these are just some pragmatic aspects, so I don't think I'll go through them. So in conclusion, we employ skeleton-based semi-explicit and explicit approaches to parallelism, and we've noted that the near best runtimes actually are achieved by using the highest level of abstraction in each of the language. So we started with an optimized sequential. We found that starting with an optimized sequential program is important, and then parallelize that. But in the end, we try to use improved features only after parallelization in the F# and Scala version to try to further improve performance. But we did that in a safe way, so not to have any kind of resolution. So so what we can say is that Haskell provides a least intrusive mechanism for parallelization, and F# provides the preferred mechanism for data parallelism with a SQL-like pinning. in the case of Scala, extra programming effort using actor-based model isn't really justified because just using the parallel collection gives okay performance. So yeah, so basically what we this is like some future work that we plan to do. Like it is to show that this is a result on cluster version, which is done by the group of Eden group in Marburg. So it shows that we can easily use the same Haskell code and just make just one or few lines code of changes to make the program run on cluster of multi-cores. So as you can see, this is the runtime of using the naive fault-based algorithm, but the plan is to try to use the Barnes and Hart algorithm using Eden on Eden as well, and you get some measurements there. So there are more details in the paper. What I did, I just covered some of the main points, but the full paper and the sources are available at this address, and any feedback or comments is welcome.
So we may squeeze in one or two questions.
Did you consult with F# or Scala experts to audit your code and see if perhaps there's something that you could have been doing better?
Yes, I did, but it was difficult to get proper help from the high performance committee of these two languages.
Okay, and then why not closure?
Well, we use Haskell and F#, which is more like an ML-like language, and Scala, which is more coming from a Java background. I mean, it's kind of like these are like the free modern functional.
You're a type bigot?
So yes.
So no types means not a functional programming language. Is that what you're saying?
Sorry?
You should just give the answer to the language shootout guy gives, which is, if you want your language included, please submit the benchmark.
Yeah. Because it was like Haskell, it was easy to translate the Haskell code into F# and the same to Scala. I'm not sure about closure, I haven't used it before.
No, but it's a challenge, it's a 6-hour challenge.
You should put that in your title.
But actually, we have a web page collecting all these results. So
Yeah, because
submit
for this work we looked at these 3 particular languages only, but there is a multi-core challenge which also has results from many other languages implementing the n-body problem.
So that's one very good question.
So I won't heckle, but how close is the Haskell performance to C with OpenMP in that challenge?
Well, the C definitely is faster by a factor of 3 to 4 times than the Haskell version, but the Haskell version that I've shown is a pure implementation. So if you use the C implementation, I just had to do one single line code of change to introduce parallelism, and you won't be able to do that in C, for example. So our aim was mainly to show how you could use only few features and then easily introduce parallelism.
Okay, thank you.